All right. So today we'll be checking out how binary cross entropy works and why this formula on screen right here is such a big deal. Now, the idea is we use this formula everywhere, pretty much in every machine learning algorithm. Either it's binary cross entropy or it's just normal cross entropy for like multi um, outputs and labels and things like that. So the problem is most people don't know where this formula comes from and kind of take this as an axiom and just assume that this is the way and this is just the right way to do it because it just works, right? It just works in most cases. And I was part of these people until like a few weeks back. But now I've learned how this works and I'll probably make this video quick. It's a short video. Quickly, we'll go through how this works and we'll derive why this is the case. There are around three things we need to worry about while trying to derive this. So firstly, we need to know what Bernoulli trials are. So Bernoulli trials are simple. It's basically things that have two outputs. So a coin toss or things where it's either success or failure, basically. So let's say if this represents one, then this represents zero. So let's take a coin toss. So if we have a coin and we toss it up, we can either get heads or we can get tails, right? And the probability of heads, as we know, is half, and the probability of tails is half as well. Now, the idea is that these are independent events. So if I take the coin for a second time and if I toss it, it remains the same. So probability of heads is still 1.1 by 1 by 2. Probability of tails is still 1 by 2. So the good thing about independent events is that let's say this is toss 1 and this is toss 2. So good thing about independent events is that we can use this concept called P is equal to P of A and P of B. It's just a simple multiplication. So if I take an example of, hey, what's the probability I get heads on the first trial and tails and heads in the second trial as well? So that becomes P of H, P of H. That equals 1 by 2, 1 by 2. That becomes 1 by 4. So it's pretty straightforward and it's not too complicated. So that helps. Now, how does this help and how does this all tie back into AI and binary category classification and things like that? So when we have to define Bernoulli trials, if let's say we know that probability of something happening and probability of something not happening, if you add them, you get one, right? So we can always write P dash as 1 minus P, right? So if we define a probability density function for a Bernoulli trial, we can kind of say that, let's say, uh, P is the probability of success, then 1 minus P will be the probability of failure. Pretty straightforward, I guess, because if you toss a coin, if you have 0.5 chance of getting a head, then you have 0.5 chance of getting a tail. If it's a biased coin and you say you have zero point 0.6 um, probability of getting a head, then you have zero point 0.4 probability of getting a tail, and so on and so forth. Now, when you say that you have a data set, you can take any example really. You can go for something like a dog versus cat or pretty much anything that's binary. The idea is that you essentially have a data set which you train on where it's a set of inputs xi and each of them have a label where I goes from 0 to n number of samples. So n is your size of data set. Each of these are your inputs and these are your labels. Now, yi can either be 0 or 1 because we're talking about binary classification, right? So you have this associated to one class and you have this associated to another one. So this is class 1, this is class 0. And it's pretty straightforward till here. Now, let's try to see how we can end up in this equation essentially. So all these points, all these data points xi are independent because uh, we can take a simple example if you want. where essentially, let's say the data set is of the form 0, comma 1, um, 1, comma 1, 2, comma 1. Um, I'll just write it on the next line because I'm running out of space. 3, comma 0, 4, comma 0, and 5, comma 0. Yeah. So it's a pretty simple data set. I mean, you can see that X i's are essentially 0, 1, 2, 3, 4, 5, and your Y i's are 1, 1, 1, 0, 0, and 0. So the function you're trying to approximate here is something like 1 when X less than or equal to 2, and 0 when X is greater than 2. Simple. I mean, it's a very simple function. Obviously, you're not going to use a neural network to learn this, but you can obviously just tell this by just looking at it. But if we had to define this in terms of uh, probability, right? Essentially, if you want to train a neural network to learn something like this, let's go back to our initial data set, this one. Um, Essentially, the probability, we are trying to find the probability density of how likely is it to get yi given xi in a data set. And that's what we're trying to, that's what AI is all about, right? It's about probabilities. So if we had to define this, so probability of your entire data set giving your entire labels, right? That becomes P of xi, let's say P of x of 0, P of x of 1, P of x of 2, P of x of 3, and so on and so forth until P of xn. The reason this is true is because all of these are independent numbers. Just like here, you can see 0, 1, 2, 3, 4, 5, and all of these are independent events. Each have its own label. So it's not like they have some relationship with each other, right? Just because 0 has 1 doesn't have any relationship with 1 having 1. Uh, like they're independent terms. So we know that the net probability is going to be this because that's basically, it's just an extension of this formula, because if it can work for 2, it can work for n, and you get the idea, right? Now, if we had to write this in scientific terms, or like, if you want to look cool doing it. So one way to do this is probability of estimating y becomes, I hope that's clear, because this is just the scientific notation for multiplication, just like how summation is sum. Uh, this one is for product. So that's just a symbol. It's nothing. It's not that deep. But now comes the fun part. We always use this term in AI, that's log loss, and we don't really, when we say loss, we imply log loss. And we can also see that the logarithm appears even in the formula of your cross entropy. Now, where does all this come from, right? We know that log of A, B, C equals log A plus log B plus log C. And that's just a property of the logarithm, and I didn't really invent anything there. So let's take this equation as 1 and let's apply log on both sides. So log probability is equal to log of P of x of 0, P of x of x1, and so on until P of xn. Again, if we compare this with this, we can see that the multiplication becomes an addition. So this becomes log of P of x naught plus log of P of x1, and so on plus log of p of xn. Now, again, if we had to write this scientifically, we can obviously write this as log probability of y equals summation of log of xi, right? That makes sense, right? And we'll leave this here and let's come back to this in a bit. I'll tell you the reason why. Um, if if we had to so right now we are leaving this as probability, right? But we need to replace that with a probability density function or some function that essentially estimates this probability, right? When we have a Bernoulli trial, if we had to write a probability density function, it looks like this, where you have p, sorry, you have 1 minus p and p. Just by notation, we always keep the success as p and the failure as um, 1 minus p. So essentially for all the labels which are 1, it's probability p, and all the labels which are 0, it's 1 minus p, the probability. If we had to write this function as a formula, it looks something like this, right? Because if you substitute x as 0, you get 1 minus p, because and we substitute p of x equals 1, we get p. And uh, that is basically what it means on top as well. So if we had to write the probability density function, we can write it as this. And that's pretty straightforward. I guess you get the idea of, like, where it comes from. This is the probability of x, right? Let's plug this into this and see what happens. Before that, we should also know another property of the logarithms, that if you have log a power x, that becomes x log a. Again, that's just another property of logarithm, just like the one on top. So when we come back to the original equation, we reach a point where we can write summation of, I'm just gonna write it here because, like, I hope that was obvious anyway. Um, Log, and instead of p of x, we'll actually write the function. That is p power x and 1 minus p, 1 minus x, right? We already know log a log b equals log a plus log b, and log a power x equals x log a. So if we had to expand that, we can say I equals 0 and log p power x plus log 1 minus p for 1 minus x. And this is the log prop. If we simplify this, if we put this formula in here, we can see that log equals summation of I equals 0 to n xi log p plus 1 minus xi log 1 minus p, right? Then again, xi and yi are just, just placeholders. I just wanted to derive it and show it to you how it works. But you see this formula, and I think you already know where I'm going with this, because essentially, uh, this is where our predictions, this is basically the formula of uh, your binary cross entropy. Because if we go up, this is where we started, and we can clearly see that the formula we have here is the same formula that we have over here. And that's pretty that's pretty neat as to how it works. The reason being, it's literally just a probability density function. Now, the idea is these y's are your label, right? And These are your individual probabilities which you're going to predict. So if you just rearrange this equation and uh, essentially find it for a data set, you basically end up with your original formula of binary cross entropy. Oh yeah, also the 1 by n is just a uh, it's just scaling. It's just a scaling factor so that the value doesn't explode and become too much because your data set size, this can be like really, 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 really huge when it comes to big data sets. And you don't want this value to be exploding after you sum the whole thing up. So you just divide it by n so that, things remain sane. And the negative is so that you move in the direction of reducing uh, the loss because you want to minimize the loss function over time, right? You want to minimize the error that's being propagated over time. So that's the reason why you have the negative sign there. But I hope this built some intuition as to why we use this formula and where it comes from and how does probability and all these like funny things just come together and somehow just work together to like get you something so cool and so simple yet something that's so like effective, right? And yeah, that's pretty much it for the video. I hope it was cool. And about the code, I'm sure nobody needs me to write the code for binary cross entropy. It's pretty straightforward, and most libraries like Torch and TensorFlow already support it internally. So I think that's taken care of. And yeah, all right, cheers.